Hello. You're listening to Night Cosmos Sleep. More than 1,000 light-years from Earth, NASA has discovered two planets nearly the size of Jupiter, yet with masses so low that their densities have been compared to cotton candy. They are not actually made of sugar, nor are they hollow spheres, but the matter inside them is spread so thinly that scientists have had to reconsider how giant planets are formed. Even more strangely, no one has ever seen these two worlds directly. They were discovered only through the faint dimming of a distant star's light. So how does NASA determine the size, mass, and density of planets that cannot be seen? And what is truly hidden inside these enormous worlds, as light and airy as cotton candy? Before we meet these two planets, we first need to visit the star they quietly orbit. Far beyond our solar system, in a region of the sky where the human eye could never distinguish individual worlds, there is a star known as TOI 791. From Earth, it appears as nothing more than a tiny source of light among countless others. It has no clearly visible disk, like the Sun, no rays strong enough to warm a distant landscape, and no obvious sign that extraordinarily unusual planets are quietly orbiting around it. The star lies approximately 1,113 light-years away from us. A light-year may sound like a measurement of time, but it is actually a unit of distance. It describes how far light can travel in 1 year. Light moves at nearly 186,000 miles per second, or about 300,000 kilometers per second, a speed so great that, in a single moment, it could circle Earth several times. Even so, the light from TOI 791 still takes more than 1,000 years to reach the world where we live. This means that when a telescope captures light from this star, we are not seeing it as it exists today. What appears in the data is an image of TOI 791 from more than 1,000 years ago, at the exact moment those rays of light first left the star. In astronomy, looking farther away also means looking deeper into the past, because light always needs time to cross the enormous distances between celestial bodies. When those rays began their journey toward Earth, the human world was very different. Many generations had not yet been born. Modern telescopes did not exist, and no one could have known that at least two planets were orbiting a distant point of light. Over the next millennium, cities were built and transformed, civilizations developed, and humanity's understanding of the sky gradually expanded. All the while, the light continued its silent passage through interstellar space. The space between TOI 791 and Earth is not completely empty, but the matter within it is so thinly scattered that it is difficult to imagine through ordinary experience. The rays of light pass through regions of extremely diffuse gas and dust, cross distances many times greater than the entire span of our solar system, and continued toward a small planet orbiting another star. Behind them, TOI 791 continued to shine, while the planets around it continued moving along their orbits. TOI 791 is the host star of this planetary system. A host star can be understood simply as the star at the center of a system. It provides most of the light and energy, while using its gravity to keep the planets moving around it. Our solar system is also a planetary system of this kind. The Sun is its host star, while Earth, Mars, Jupiter, and many other objects travel through the region of space held within its gravitational influence. TOI 791 has a family of its own, but the members of that family are not easy to see. A star produces its own light, while a planet reflects only a very small portion of the light it receives. At a distance of more than 1,000 light-years, the light reflected by a planet becomes incredibly faint and is almost completely overwhelmed by the brilliance of its host star. Because of this, even very large planets can remain hidden within the star's light for a long time. To human observers, TOI 791 once appeared to be nothing more than a solitary point of light. There were no images showing planets orbiting around it, and no clear outlines separating those worlds from the surrounding darkness. By looking with the naked eye or through an ordinary telescope, we would never know that enormous planets were moving there. To discover them, astronomers had to observe not the planets themselves, but the tiny changes those planets left behind in the star's light. Some of the light from TOI 791 eventually entered the instruments of the TESS Space Telescope. TESS is a NASA telescope designed to monitor the brightness of large numbers of stars over extended periods. It does not need to see a planet clearly. It only needs to detect whether a star's light has changed in a particular way and whether that change happens again. At first, the light from TOI 791 appeared stable. The star did not suddenly flare or noticeably fade. It simply continued shining like countless other stars in the sky. But when the data was observed for long enough and measured with enough precision, extremely faint dips began to appear within that seemingly steady stream of light. The changes were so small that the human eye could never detect them without sensitive instruments and the proper methods of analysis. A star can change in brightness for many reasons. Darker regions may appear on its surface. The star itself may pulse or fluctuate. Light from another nearby star in the sky may also complicate the measurement. For this reason, a single drop in brightness is not enough to prove that a planet exists. Astronomers must continue watching, compare many observations, and search for a repeating pattern that can be explained by orbital motion. In the case of TOI 791, the dimming events carried the signature of very large objects. When a planet moves into a position between its star and the telescope, it blocks a portion of the light traveling toward Earth. This does not mean that the star itself actually becomes dimmer. Only part of its glowing surface is temporarily hidden by the planet from our point of view. A planet does not need to produce light in order to be discovered. It only needs to leave behind a shadow. From more than 1,000 light-years away, the shadow of an entire giant world appears in the data as nothing more than a slight downward curve. But by learning how to read that signal, scientists can gradually estimate the size of the object that passed in front of the star, the time it takes to complete an orbit, and its approximate distance from the star. What is remarkable is the contrast between the enormous scale of the planet and the tiny trace it leaves behind. A world may stretch across tens of thousands of kilometers and be surrounded by layers of gas extending far into space. Yet from this distance, the entire planet causes the star's brightness to decrease by only a very small amount. A gigantic object is revealed not through a sharp and detailed image, but through a delicate change in light. Those changes open the doorway into the TOI 791 system. Astronomers began investigating the source of the signal, tracking the moments when the brightness decreased, measuring how long the star remained partially obscured, and waiting to see whether the event would return. Each new observation added another piece to the puzzle, helping researchers eliminate other explanations and making the possibility of a planet increasingly clear. But the data did not contain only one repeating rhythm. Within the light of TOI 791, there appeared to be two different patterns of change, occurring at different intervals. This suggested that the distant star was not being crossed by only one planet. At least two worlds seemed to be orbiting it, each leaving behind its own distinct signature. At this point, their sizes, masses, and internal structures had not yet been revealed. We were standing only at the edge of the discovery, where a point of light that had once seemed solitary was beginning to show that it was surrounded by an entire system moving quietly through space. From just a few subtle changes in brightness, a much larger story about two distant planets was slowly beginning to emerge. That light had traveled for more than 1,000 years, almost entirely uninterrupted. But just before beginning its long journey toward Earth, part of it had been blocked by an enormous object. From Earth's point of view, the two planets orbiting TOI 791 are completely lost in the light of their host star. They are too distant, too dark, and appear too close to the star in the sky for a telescope to easily separate the image of one world from another. Even when that region of space is magnified, all that appears is a single point of light. There are no visible planetary outlines, no surfaces, and no enormous cloud formations clearly revealed before our eyes. But to discover a planet, astronomers do not always need to see the planet itself. Sometimes, they only need to notice what happens to the light when the planet passes in front of its star. That is the work of TESS, a space telescope launched into orbit by NASA to search for planets beyond our solar system. Its full name can be understood as the Transiting Exoplanet Survey Satellite. An exoplanet is a planet that orbits a star other than the Sun, while a transit occurs when a planet passes in front of its star from our viewing angle on Earth. TESS does not operate like a camera trying to capture close-up images of individual planets. Instead, it spends its time monitoring the brightness of many stars at once. Each star is observed as a small source of light, while the telescope continuously records whether that light remains steady or changes over time. Most of the time, a star's brightness remains relatively stable. However, if a planet happens to pass between the star and TESS, it blocks a small portion of the light traveling toward the telescope. The star itself does not truly become weaker. It continues producing energy just as it did before. From our perspective, however, part of its glowing surface has been temporarily hidden by the planet. We can imagine a lamp shining at the far end of a very large room. If a butterfly flies across the front of the lamp, we may not be able to make out its wings, its colors, or its shape. The distance makes the butterfly appear far too small, but for the brief moment when it crosses the light, the lamp may seem to dim slightly. From that change alone, we know that an object has just passed in front of the light source. For a star more than 1,000 light-years away, the change is far smaller. Even an enormous planet can block only a small portion of the star's surface. TESS must therefore measure starlight with extremely high precision. It does not wait for a star to disappear completely. Instead, it searches for gentle decreases in brightness that last for a period of time before returning to the original level. This data is often displayed as a line showing brightness over time. When no object is passing in front of the star, the line remains almost flat. As a planet begins moving across the face of the star, the line slowly dips downward. When the planet is positioned most deeply in front of the glowing surface, the brightness reaches its lowest point. Then, as the planet moves away from the opposite side, the light increases again, and the line returns to its earlier position. On paper, the entire event may look like nothing more than a small dip in a long line, but that dip is the trace of an enormous journey. It records the moment when a world completes part of its orbit, passes in front of its star, and sends its shadow across more than 1,000 light-years before human instruments finally measure it. TESS cannot see what color the planet's atmosphere might be. It cannot tell us whether the world is covered by cloud bands like those of Jupiter or hidden beneath a thick layer of haze. Nor can it look inside the planet to determine whether its core is made of rock, ice, or other heavy materials. During the earliest stage of discovery, TESS records only 3 very simple states: the star shining normally before the planet passes, its light dimming slightly while the planet blocks part of the glowing surface, and the brightness returning to normal after the planet has moved away. Although they seem simple, these 3 stages contain a great deal of information. The amount by which the light decreases allows astronomers to estimate how large the planet is compared with its star. A small planet blocks only a tiny portion of the glowing surface, so the brightness drops only slightly. A larger planet blocks more light, creating a deeper dip in the graph. This does not mean that TESS can immediately determine the planet's exact diameter from a single observation. Scientists must first understand how large the host star is. If the same object passes in front of a small star, it will block a greater percentage of the light than it would while passing in front of a much larger star. The planet's size must therefore be calculated in relation to the size of the star it orbits. We can imagine 2 identical coins held in front of 2 lamps of different sizes. In front of the smaller lamp, a coin might block nearly all the light. In front of the larger lamp, it would create only a small dark area. The coin itself has not changed, but the proportion of light being blocked is completely different. Astronomers must make a similar comparison, when interpreting the transit signal of a planet. The depth of the drop in brightness provides a clue about size, but it does not reveal how much the planet weighs. Two objects can block the same amount of light if they are similar in size, even if the amount of matter inside them is very different. A solid sphere and a sphere containing a great deal of empty space might cast identical shadows. For this reason, the transit method alone cannot tell scientists whether a planet has a large or small mass. At this stage, the shadow answers only one question: how wide is the object passing in front of the star compared with the glowing body behind it? The question of mass requires a different kind of evidence, one connected to gravity and the ways the planets affect one another's motion. But before searching for that evidence, the research team first had to be certain that the dimming events truly came from planets. Not every decrease in a star's brightness is caused by a transit. A star may naturally change in brightness because of activity on its surface. Two stars orbiting each other may also take turns blocking one another's light. A faint background star could appear close to TOI 791 along the same line of sight, producing a signal that might easily be mistaken for a planet. The instruments themselves may also record noise or small errors unrelated to any real world. For this reason, what matters is not only that the light decreases, but also the shape of the decrease and whether it repeats. A planet traveling along a stable orbit will return after an almost regular period of time. Each time it passes in front of the star, the light curve should dip to a similar depth and remain dimmed for a similar length of time. When the same pattern appears again and again, it becomes far less likely that the signal is merely random noise. The shape of the dip carries information of its own. When the planet first begins to cross the edge of the star from our point of view, it blocks only a very small portion of the glowing surface, so the light decreases gradually. Once the entire planet is positioned in front of the star, the decrease becomes more stable. As the planet begins to leave, the light also rises gradually instead of returning all at once. The complete event creates a smooth curve, reflecting the continuous motion of a round object crossing in front of a larger source of light. The duration of the event can also help astronomers understand the path the planet takes across the star. A planet passing close to the center may take longer to cross the entire glowing surface. If it only skims near the edge, the period of dimming may be shorter. These conclusions, however, must be combined with information about the orbit, the size of the star, and many other factors. Astronomers cannot simply look at one dip and immediately understand the complete structure of the system. TESS performs this work with patience. It does not look at a star for only a few seconds before moving on. The telescope monitors an entire region of the sky over an extended period, continuously collecting arriving light. Within the enormous stream of data, analysis programs search for patterns of dimming that may repeat. Scientists then examine each signal, compare it with other observations, and eliminate possible sources of confusion. In the case of TOI 791, a single extended dimming event did more than suggest that an object had passed in front of the star. The depth of the shadow indicated that the object was not small. It blocked a significant portion of the star's light, enough for the research team to begin considering the possibility of a giant planet. But one deep shadow was not complete evidence. They still needed to see it return. Waiting for a signal to repeat is an essential part of the transit method. If a planet completes an orbit in 3 days, its shadow may appear many times within only a few weeks. The data quickly forms a clear rhythm, but if a planet takes several months to complete a single orbit, each transit, if TESS is not observing that particular region of the sky at the right moment, the entire event may pass without being recorded. This is one reason planets with short orbits are easier to discover. They orbit close to their stars, move quickly, and frequently pass in front of them. During the same observing period, TESS may detect several transits, allowing astronomers to confirm the orbital period relatively quickly. Planets farther away require more time, and every return of their shadow becomes a rare opportunity. The light from TOI 791 produced one clear decrease in brightness. After the planet moved out of our line of sight, the light curve returned to normal. The shadow was gone. The star once again shone steadily, as though the earlier event had never occurred. Astronomers knew that if this truly was a planet, it was continuing around the star through a part of its orbit that could not be detected from Earth. For most of its journey, it was not positioned between TOI 791 and our planet, so it produced no transit signal. The telescope could only wait for the world to complete its orbit and return to the same position. Day after day, the light remained stable. 1 week passed, followed by several more, without another appearance of the shadow. This suggested that the newly detected world was not orbiting extremely close to its star, as many familiar exoplanets do. Its orbit appeared to be wider, and its journey back across the face of the star would take longer than initially expected. The first shadow detected by TESS did not return after only a few days. It forced astronomers to wait for many months. After the first decrease in brightness, TOI 791 returned to its steady state. The object that had just crossed in front of the star moved out of Earth's line of sight and continued along the rest of its orbit. TESS could no longer see its shadow. The telescope could only continue watching and wait. If the object truly was a planet, a similar period of darkness would have to appear again when it completed another journey around the star. The amount of time needed to complete one full revolution is known as the orbital period. Earth has an orbital period of about 1 year. Mercury, which lies closer to the Sun, needs only about 3 months. Planets farther away usually take longer because their orbits are wider and they move more slowly around their stars. Many of the exoplanets discovered by TESS orbit extremely close to their host stars. Some worlds need only a few days to complete a full revolution. During a single month of observation, their shadows may repeat many times, creating a clear series of signals. Astronomers can quickly recognize the regular rhythm and estimate the planet's orbital period, but the object orbiting TOI 791 did not return so quickly. 1 week passed, followed by many more. The star's brightness remained almost unchanged. The shadow that had appeared in the data did not return after a few days, nor did it return after a month. This suggested that the planet was traveling along a wider orbit than most of the short-period worlds TESS can detect so easily. Finally, about 139 days later, the light from TOI 791 dimmed again in a familiar pattern. The depth of the decrease closely resembled the earlier event. The amount of time the star remained dim was also similar. When the planet moved away from the face of the star, the brightness gradually returned to its original level. The shadow had completed a full orbit. From 2 appearances, separated by nearly 139 days, scientists could begin determining the orbital period of this world. It was named TOI 791b, the inner planet of the system. The letter B is usually assigned to the first planet confirmed around a star, while the star itself is considered component A. A period of about 139 days is equal to more than 4 months on Earth. For a human being, that may not seem like an especially long time, but in a search based on the transit method, 4 months can create many difficulties. The telescope must be observing the correct region of the sky at the exact moment the planet passes in front of its star. If the observation ends only a few days too early, or if TESS is pointed toward another area, the entire event may be missed. The planet completes its orbit whether humans are watching or not. Its shadow exists for only a brief period compared with the length of the entire revolution. During most of those 139 days, TOI 791b occupies positions where it does not block the star from Earth's point of view. TESS may continue collecting the star's light, but it will detect no sign of a transit. We might imagine the hand of an enormous clock moving very slowly around its face. At only one position does the hand pass across a small point of light. That moment quickly passes, and the observer must wait for the hand to complete an entire circle before it returns. For this reason, Detecting a single decrease in brightness and confirming a planet are two different things. The first dimming event reveals only that something has blocked part of the star. The event may have been caused by a planet, but it could also have come from another source or from an error in the data. When the same signal returns after a consistent interval, the planetary explanation becomes far more reliable. Even two transits are not always enough to fully understand an orbit. Astronomers want to observe additional events because every new transit allows them to measure the period more precisely. If the first and second events are separated by 139 days, but the third appears slightly early or slightly late, that difference may contain important information. It could be the result of a measurement error, but it might also indicate that another object is exerting a gravitational influence. The difficulty is that TESS does not continuously observe the same star for many years. The telescope surveys different regions of the sky according to a planned schedule before moving on to another area. To capture more transits from a planet with a long orbital period, it must return to the region containing TOI 791 at a later time. Each return creates another opportunity, but there is no guarantee that the planet will cross the face of the star while the telescope is watching. Because of this, the story of TOI 791b was not completed in only a few days. Data had to be collected across several observing periods. Scientists compared the decreases in brightness recorded at different times, checking whether they had the same depth, lasted for the same amount of time, and belonged to the same orbital cycle. Each transit was like a marker placed along an invisible orbit. A single marker could not reveal the shape of the entire circle. Two markers began to expose the rhythm of the motion. As more markers appeared, the orbital period became clearer, and even the smallest differences slowly began to emerge. TOI 791b was therefore identified not through a single moment, but through repetition. The planet left its shadow behind for only a very small part of its journey, then disappeared from the data for more than 4 months. The patience of the observers had to stretch across the same span of time that the distant world needed to travel around its star. While astronomers waited for that darkness to return, another decrease in brightness appeared, but it did not belong to the first planet. As the roughly 139-day cycle of TOI 791b gradually came into view, astronomers thought they had identified the main rhythm hidden within the star's light. But between the transits believed to belong to this planet, another decrease in brightness appeared. It did not occur when TOI 791b was expected to cross in front of the star, and its shape was not entirely the same as the earlier signals. At first, one unusual dimming event was not enough to conclude that another planet existed. It could have been caused by a natural change in the star, noise in the data, or another source of light located nearby along the same line of sight. The new signal therefore had to be examined separately rather than forced into the known 139-day cycle. If this decrease belonged to TOI 791b, it should have appeared close to one of the times predicted from the planet's orbit. But the new shadow arrived either too early or too late to fit that schedule. It also blocked more light, suggesting that the object responsible for it might be larger than the first planet. The possibility of a second world began to emerge. The researchers separated the decreases in brightness into two groups. The first consisted of signals with similar depths that repeated about every 139 days. These were the transits of TOI 791b. The other group was deeper and appeared over a longer interval. When the observation dates were placed side by side, the second sequence revealed a repeating rhythm of approximately 232 days. The world producing this slower rhythm was named TOI 791c. The letter C indicates that it was the next planet identified in the system after TOI 791b. It moves along the outer orbit and therefore needs more time to complete one journey around the host star. A period of about 232 days is equal to more than 7 months on Earth. During most of that time, TOI 791c occupies positions where it does not pass in front of the star from our point of view. TESS continues receiving light from TOI 791, but no shadow from the outer planet appears. Only when that world returns to the exact position between the star and the telescope does the light decrease once again. Recognizing the two planets required astronomers to follow two different clocks within the same stream of data. One completed its orbit in about 139 days. The other needed approximately 232 days. When viewed as isolated events, the decreases in brightness might have seemed irregular. But once arranged according to their proper cycles, they separated into two distinct rhythms. We can imagine two hands moving around the face of a very large clock. The first hand travels faster and crosses a small point of light more often. The second moves more slowly, so the interval between each of its appearances is longer. Whenever one of the hands passes across that point, it blocks a different amount of light. By measuring the depth of the shadow and noting when it appears, an observer can determine which hand has just crossed. The shadow of TOI 791c was deeper than that of the inner planet. This meant that it covered a larger portion of the star's surface and was therefore larger than TOI 791b. At this stage, however, the transit signals only allowed astronomers to compare their sizes. A larger shadow did not automatically mean that the object producing it contained more matter. The masses of the two planets remained unanswered questions. The discovery of the second planet changed the entire view of the TOI 791 system. This was no longer a star, with only one giant world moving around it. It was a system containing at least two large planets, both following relatively long orbits and both happening to cross in front of their star from Earth's point of view. This kind of alignment does not always occur. For a planet to transit, the plane of its orbit must appear almost edge-on from our viewing angle. If the orbit tilts upward or downward beyond a certain degree, the planet passes above or below the star and never blocks its light. The planet still exists, but the transit method cannot detect it. In the TOI 791 system, both orbits are aligned in a way that allows the two planets to pass in front of the star one after the other. Because of this, TESS can record the shadows of both worlds. This creates a special opportunity. When several planets transit within the same system, astronomers can measure not only the individual period of each world, but also the ways in which they influence one another. The two transit sequences also strengthen the conclusion that the signals came from the same planetary system. TOI 791b travels along the inner orbit and completes its journey more quickly. TOI 791c lies farther away, moves more slowly, and produces a deeper decrease in brightness. Both pass in front of the same star, but each world leaves its own distinct signature in the light. Later observations gradually made the two rhythms clearer. Whenever a new event appeared, the researchers examined whether it fell closer to the 139-day schedule or the 232-day schedule. They compared the depth, duration, and shape of the decrease with earlier events. With each new piece of data, the two invisible orbits slowly began to take form, but the long orbital periods also made confirmation more difficult. During one Earth year, the inner planet completes only a little more than 2.5 orbits, while the outer planet does not even complete 2. To collect more transits, astronomers had to gather data over several years and combine observations made at widely separated times. Every event was therefore extremely valuable. Missing a single transit of TOI 791c could mean waiting more than 7 months for another opportunity. If poor weather interfered, an instrument malfunctioned, or the star was outside the field being observed, the shadow could arrive and disappear without leaving behind a complete record. The length of each transit created another difficulty. The two planets not only needed many months to complete their orbits, once they began crossing in front of the star, they also required many hours to move across the entire glowing surface. From the moment the shadow first touched one edge of the star until it moved away from the opposite side, nearly half a day could pass. The problem was that each transit lasted almost half a day, so long that it was extremely difficult for a single ground-based observatory to follow the entire event from beginning to end. A transit becomes truly useful when astronomers can observe it long enough to determine when the light begins to fade, where it reaches its lowest point, and how it returns to normal. For TOI 791b and TOI 791c, this work was especially difficult because each planet needed more than 11 hours to cross the face of the star from Earth's point of view. 11 hours is nearly half a day. During that amount of time, the sky above an ordinary observatory can change completely. A star that is high in the sky at the beginning of the night may gradually sink and then disappear below the horizon. Somewhere else, daylight may arrive before the planet has finished crossing the star. In that case, a telescope may record only the beginning or the end of the event. An incomplete transit still has value, but it leaves many gaps. If astronomers observe only while the light is already decreasing, it is difficult to determine the exact moment when the planet began moving in front of the star. If the telescope starts observing after the planet is already crossing the glowing surface, the beginning of the light curve will be missing. And if dawn arrives too early, the moment when the planet leaves the star's face may never be recorded. To fully understand the shape of a transit, astronomers need a night that is long enough. And on Earth, there is one place where winter can extend the darkness for many continuous hours, or even for many days. In Antarctica, the sun can remain below the horizon for an exceptionally long time. Instead of a short night confined between sunset and sunrise, observatories there can operate beneath a continuously dark sky. This environment is especially well suited to astronomical events lasting nearly half a day, such as the transits of the two planets orbiting TOI 791. In the middle of that vast expanse of ice stands the ASTEP telescope. It is an observing instrument built to operate in the cold and isolated environment of Antarctica. It cannot travel closer to the TOI 791 system, nor can it see the two planets directly. Its work is still to monitor the star and measure extremely small changes in its light. But ASTEP's advantage lies in time. Once a transit begins, the telescope can continue observing for many hours without having to stop because the sun is rising. The star may also remain in a favorable position in the sky for longer than it would at many other locations. As a result, an event lasting more than 11 hours has a chance to be recorded almost in its entirety. We can imagine a small observatory dome standing in the middle of the dark ice. A white landscape stretches in every direction, but during the night, the horizon nearly disappears into the darkness. Above the dome, TOI 791 is nothing more than a very faint point of light. No one standing below could see the planets moving around it. Yet the instrument continues collecting tiny amounts of light that have traveled more than 1,000 light years. When a planet begins to pass in front of the star does not suddenly become dim. Its brightness decreases very slowly. During the first few hours, only a small portion of the planet overlaps the edge of the star. Then the shadow moves farther across the glowing surface, reducing the amount of light being received. Near the middle of the transit, the decrease approaches its lowest level and remains there for a period of time before gradually rising again. The entire change is so subtle that, to the human eye, the star would appear no different than before. But to the measuring instrument, every minute leaves another point on the graph. Hundreds of data points follow one another, forming the complete shape of the shadow as it moves from one side of the star to the other. Recording all three stages is important. The beginning reveals when the planet first starts blocking the star. The middle helps determine the greatest reduction in brightness. The final stage shows when the planet has completely left the glowing surface. From these moments, researchers can measure the duration of the transit and determine whether the signal is consistent with a planet. The Antarctic data does not stand alone. Observatories in other parts of the world also point their telescopes toward TOI 791 whenever conditions allow. One location may record the beginning of a transit, Another may follow its middle. A different observatory may capture the final portion when the star becomes visible in its sky. The results can then be placed beside one another to create a more complete picture. This cooperation also helps confirm the source of the signal. If the dimming appears only in the data from one instrument, it may have been caused by noise, weather, or a technical problem. But when several telescopes in different locations record the same decrease at the expected time, the evidence that it was a real event becomes much stronger. Ground-based observations also help determine whether the shadow truly comes from 2I 791. Within one region of the sky, many stars may appear very close together from Earth, even though they are actually separated by enormous distances. Their light can sometimes become blended in data from an instrument with a wide field of view. A pair of faint background stars may eclipse one another and create a signal that resembles a planet passing in front of a star. Ground-based telescopes can examine the surrounding region using different methods and determine which star is actually becoming dimmer. If the decrease appears at the exact position of TOI 791, the idea that planets are orbiting this star becomes stronger. But if the signal comes from a nearby source of light, the original explanation must be reconsidered. Every complete transit also makes the timing more precise. Astronomers need to know not only the day on which the event occurs, but also the exact moment when the shadow crosses the middle of the star. Even a small error in this measurement can affect the calculated orbital period. As data accumulates over many years, these precise times can reveal whether the planet always arrives according to schedule. This work requires patience. A transit of TOI 791b returns only about once every 139 days. For TOI 791c, the waiting period is approximately 232 days. If one event is missed, the next opportunity does not appear the following night or even the following week. Observing teams may have to wait for many months before the planet returns to the correct position. For this reason, every observing night must be planned carefully. The predicted time is calculated in advance. The telescope is pointed toward the star before the transit begins. Observations often continue both before and after the event, so astronomers can establish the star's normal level of brightness. If measurements are taken only after the light has already decreased, there will be no reliable baseline for determining how deep the dimming truly was. In Antarctica, the work also comes with extreme cold and isolation. The equipment must withstand very low temperatures, while repairing or replacing a component is not as simple as it would be at an observatory near a city. Many operations must be automated and monitored remotely. Yet this harsh environment provides the long stretch of darkness that the observations require. An event occurring more than 1,000 light-years away is therefore followed from several locations on one small planet. TESS observes from space, unaffected by clouds or the cycle of day and night in the same way as ground-based telescopes. ASTEP takes advantage of the long Antarctic night. Other observatories add data from different locations and time zones. No single instrument provides the complete answer on its own. TESS discovers the decreases in brightness. Ground-based telescopes verify their source, fill in missing sections of the data, and measure the timing more precisely. When the results agree, the faint shadow within the starlight gradually becomes evidence of real worlds. The long transits of TOI 791b and TOI 791c are rare events for ground-based observers. They are difficult to follow because they require many uninterrupted hours of darkness, but they are also valuable because each event contains a great deal of information about the planet's orbits and sizes. Recording an entire transit from beginning to end is like watching a door slowly open and then close again in front of the light of a star. For more than 11 hours, the shadow moves across the glowing surface. When it finally leaves, TOI 791 returns to its familiar brightness. In the Antarctic sky, The star remains nothing more than a tiny point. But within the data, the shapes of the two objects have gradually become clearer. When the sizes of the two shadows were calculated, the results showed that these were not small planets. Both were nearly as large as Jupiter. In our solar system, Jupiter is the largest planet. Its diameter is about 11 times that of Earth, and the space inside it is vast enough to hold more than 1,000 spheres the size of our planet. Place Earth beside Jupiter, and the familiar world of humanity immediately becomes a tiny dot next to the enormous cloud bands of the gas giant. So when the transit signals revealed that the two worlds orbiting TOI 791 were nearly the size of Jupiter, astronomers knew they were observing extremely large objects. These were not small rocky planets like Earth or Mars. Their shadows blocked a significant portion of the star's light, showing that both planets occupied an enormous volume. TOI 791b, the planet orbiting closer to the star, has a radius nearly equal to Jupiter's. The radius is the distance from the center of a planet to the outer boundary used when measuring its size. For a gaseous world with no clearly defined solid surface, this boundary is usually placed at the layer of atmosphere thick enough to block most of the light from the star behind it. TOI 791c is even larger. Its radius is about 15% greater than Jupiter's. That difference may not sound especially large, but when an object is already the size of a planet, even a modest increase in radius produces a significant increase in volume. TOI 791c therefore occupies a region of space larger than even the biggest planet in our solar system. If we could place all three worlds side by side, Earth would almost disappear from the scene. TOI 791b would appear as an enormous sphere nearly the size of Jupiter, while TOI 791c would extend even farther. The two distant worlds would dominate the entire image, while our planet would resemble only a tiny grain beside them. But that image would tell us only how large they are. The transit method measures the amount of starlight being blocked. A large planet creates a larger shadow, while a small planet creates a smaller one. From the depth of the decrease in brightness, scientists can estimate the area of the star covered by the planet and then calculate its radius. But the shadow does not reveal how much matter the planet contains. This is the important difference between size and mass. Size tells us how much space an object occupies. Mass tells us how much matter the object contains. Two objects can be nearly equal in size, yet have completely different masses if their internal structures are not the same. We can imagine a metal sphere and a large ball filled with air. If they have the same diameter, they will cast nearly identical shadows when placed in front of a light source. But when lifted, the metal sphere will be far heavier because the material inside it is packed much more densely. Planets are not as simple as those two spheres, and TOI 791b and TOI 791c are not hollow shells. They still contain matter, possibly including a relatively small core surrounded by extremely broad layers of gas. The comparison simply makes one point clear. A large shadow does not necessarily mean a large mass. A third concept must now be considered: density. Density describes how much matter is distributed within a certain volume. If an object contains a great deal of mass within a small space, its material is tightly packed and its density is high. If the same amount of matter is spread across a larger volume, its average density becomes lower. Earth has a relatively high density because most of the planet is made of rock and metal. Jupiter is vastly larger, but because it consists mainly of hydrogen and helium, its density is lower than Earth's. Even so, Jupiter still contains an enormous amount of matter. Its mass is hundreds of times greater than Earth's, producing enough gravity to hold onto a deep and massive atmosphere. The mystery of the two planets around TOI 791 was that they had the dimensions of giant gas planets, but no one yet knew whether their masses matched their enormous appearance. From their shadows, they resembled relatives of Jupiter, but their outward size could not reveal whether these worlds were tightly compressed or greatly inflated, whether their cores were large or small, or how much of their total structure was made up of gas. To determine density, scientists need both size and mass. Their sizes had already been estimated from the transits. What remained unknown was the amount of matter each planet carried. Normally, the mass of an exoplanet can be measured through the tiny motion it causes in its host star. The star pulls the planet along its orbit, but the planet also pulls back on the star through gravity. As a result, the star does not remain perfectly still. It makes a slight motion around a shared point. These movements, however, are not always easy to measure, especially when the system is extremely distant and the signal is weak. In the case of TOI 791, researchers had another method available. The two planets existed within the same system, and their orbits were close enough for the gravity of one world to slightly alter the motion of the other. At first glance, both planets still appeared to move steadily around the star, but when the timing of their transits was measured with enough precision, astronomers could see that they did not always arrive exactly on schedule. Sometimes a shadow appeared earlier than predicted. At other times, it arrived later. These small differences revealed that the two worlds were pulling on each other during every orbit. The more matter a planet contains, the stronger its gravitational pull becomes. The degree to which it changes the motion of the neighboring planet can therefore be used to estimate its mass. Scientists do not need to touch the distant world or see inside it. They only need to observe how it causes its neighbor to arrive slightly early or slightly late along its orbit. The two shadows had already shown astronomers how wide TOI 791b and TOI 791c were. Now, the timing of those same shadows would reveal how much matter they contained. To discover how much matter was hidden inside the two planets, scientists needed a scale. That scale was the gravitational pull between the two worlds. After determining the two orbital periods of approximately 139 and 232 days, astronomers could predict when TOI 791b and TOI 791c would pass in front of their star. If each planet were influenced only by the gravity of the host star, its future transits would occur on an almost perfectly regular schedule. Once the time of one transit and the length of the orbital period were known, the following events could be calculated. TOI 791b should have returned about every 139 days. TOI 791c should also have appeared according to its own rhythm, completing each orbit in approximately 232 days. In a perfectly simple system, the shadows would behave like the hands of a clock. Each would move at a steady rate and cross the same position at predictable times. But the data did not behave exactly that way. On some occasions, a planet began crossing the star earlier than expected. During other transits, its shadow appeared later. These differences were not merely a few seconds caused by the limitations of the instruments. In some observations, the shift approached nearly 50 minutes, large enough for the researchers to recognize that the planet's orbits were being disturbed. This did not mean that the planet suddenly stopped or began changing direction in a chaotic way. Their motion still followed the laws of gravity. But the TOI 791 system did not contain only one star and one isolated planet. Two worlds were orbiting the star, while also pulling on each other at every moment. The attraction between the planets was far weaker than the gravity of the host star. TOI 791 remained the object that determined the overall shapes of their orbits. Even so, the small gravitational pull between the two planets was strong enough to slightly change their speeds. These changes were difficult to detect during any single orbit, but when followed across many transits, they gradually formed a clear pattern. When the two planets moved into relatively close positions along their orbits, the outer world could pull the inner planet slightly forward. TOI 791b would then travel a little faster than predicted and cross the star earlier. At the same time, the inner planet would pull back on TOI 791c, slightly altering the motion of the outer world. Once the two planets moved beyond that arrangement and continued along their paths, the direction of the gravitational pull changed. A planet that had previously been pulled forward could be held back slightly during another part of the cycle. Its shadow would then appear later than calculated. Arriving early or late was not a permanent role assigned to either planet. It changed according to the positions of both worlds within the system. We can imagine two runners moving along separate circular tracks around the same field. One runs on the inner track and therefore completes each lap more quickly. The other follows the outer track and needs more time. If they had no influence on one another, each runner would cross the starting line according to a steady rhythm of their own. But in the TOI 791 system, these imaginary runners can slightly alter each other's pace whenever they reach the right relative positions. One is drawn forward by a small amount, while the other slows down. The next time they cross the starting line, their arrival no longer matches the original schedule perfectly. The small difference continues changing with each lap, leaving behind a sequence of early and late arrivals that scientists can analyze. This phenomenon is known as a transit timing variation. It is a change in the time at which a planet crosses in front of its star compared with the regular schedule that was predicted. Instead of asking only how deep the shadow was or how long it lasted, astronomers also ask how many minutes early or late it appeared. Every transit provides a point in time. When many of these points are placed on the same graph, a pattern of deviations begins to emerge. If a planet always arrives on schedule, the points remain close to a straight line. But if another object is pulling on it, the points move above and below that line in a pattern connected to the motion of the entire system. Computers are used to test many different models. In each model, researchers adjust the masses of the two planets, the shapes of their orbits, and their positions at different moments. They then calculate when every transit should have occurred under those conditions. The model that produces a sequence of early and late transits, most similar to the observed data, provides a better estimate of the system's structure. The process is like identifying two invisible objects through the ways they alter each other's motion. Astronomers cannot see gravity directly. There is no visible cord stretching between the two planets, nor is there a bright signal showing when the pull becomes stronger. They observe only the result. One shadow arrives early and another arrives late. Time itself has become the measuring instrument. Mass determines the strength of gravity. A planet containing more matter will pull more strongly on its neighbor and create larger changes in the transit schedule. If its mass is small, its influence on the orbit of the nearby world will also be weaker. The timing shifts can therefore be used as an indirect scale. Scientists do not place TOI 791b or TOI 791c on a physical instrument. Instead, they measure the effect each planet has on its neighbor and work backward to determine how much matter would be needed to produce that gravitational pull. Weighing planets in this way requires many observations. One early transit is not enough to reveal the cause. The difference may come from measurement limitations or from an orbital period that was not initially calculated with sufficient accuracy. But when the early and late arrivals repeat in a pattern consistent with the gravitational interaction between two planets, the solution becomes more reliable. The orbital periods of the two worlds also make their interaction easier to detect. 2I 791b completes its orbit more quickly, while 2I 791c moves more slowly along the outer path. After a certain number of orbits, they return to relative positions similar to those they occupied before. Each time this happens, the gravitational interaction acts in a similar direction, allowing the small differences to accumulate into a signal clear enough to measure. This is why precisely measuring the midpoint of every transit is so important. An error of only a few minutes in the data can change the estimated masses. Observations from TESS, ASTEP, and other telescopes were therefore used for more than confirming that the shadows existed. They also helped place each timing marker in its proper position. From the outside, the two planets remained objects that could not be seen directly. But within their timelines, each world was leaving evidence of the amount of matter inside it. A planet might block a large portion of the star's light and appear to be an extremely massive world. Yet only its gravitational pull on the neighboring planet could reveal whether that enormous appearance truly matched its mass. As the models were adjusted to reproduce the sequence of transits, an unusual result gradually emerged. The two planets were nearly the size of Jupiter, or even larger, but the gravitational forces they exerted on each other were far weaker than might be expected from such enormous worlds. This meant that their large sizes were not accompanied by a corresponding amount of matter. Their outer layers occupied a tremendous volume, while the total mass of each planet was far smaller than Jupiter's. And when that gravitational pull was converted into mass, the first planet, a world nearly the size of Jupiter, was found to weigh less than 10 times as much as Earth. When the gravitational models finished weighing the two worlds around TOI 791, the results looked very different from what their enormous sizes had first suggested. Their large shadows made them seem like planets in the same general class as Jupiter. But the actual amount of matter inside them was far smaller. TOI 791b, the inner planet, has an estimated mass of about 9.5 times that of Earth. It is still heavier than our planet, but it is remarkably light for a world nearly the size of Jupiter. Jupiter has more than 300 times the mass of Earth, while TOI 791b carries only about 3% of Jupiter's mass. In other words, the two planets can cast nearly comparable shadows as they pass in front of their stars, even though the amounts of matter inside them are completely different. TOI 791b occupies almost as much space as Jupiter, despite containing only a very small fraction of its mass. TOI 791c is even more surprising in terms of size. Its radius is about 15% greater than Jupiter's, making it the largest world in the system. Yet its estimated mass is only about 18.6 times that of Earth, equivalent to nearly 5.9% of Jupiter's mass. The outer planet is almost twice as massive as the inner one, but because its volume is also larger, its matter is still spread extremely thinly. It has the appearance of a giant gas planet, without containing the amount of material normally associated with a world of that size. Once astronomers knew both the sizes and masses of the planets, they could calculate their average densities. Density describes how much matter is distributed within a certain volume. The more matter an object contains within a small space, the higher its density. If the same amount of matter is spread across a larger volume, the density becomes lower. The average density of TOI 791b is estimated to be only about 0.038 grams per cubic centimeter. For TOI 791c, the figure is approximately 0.047 grams per cubic centimeter. For comparison, the density of water is close to 1 gram per cubic centimeter. This means the average densities of the two planets are only a few percent of the density of water. These numbers do not mean that the planets are completely empty inside. They still contain matter, possess gravity, and most likely have more concentrated internal regions. But when their total masses are divided by the enormous volumes occupied by their outer layers, the resulting densities become extraordinarily low. This is why worlds like these are known as superpuffs, meaning highly inflated planets. The name describes planets that are extremely large compared with their masses. They appear to be surrounded by greatly expanded layers of gas, causing their observed radii to be much larger than the region containing most of their matter. The comparison to cotton candy also comes from this unusually low density. A piece of cotton candy can appear quite large even though it contains relatively little actual sugar. Extremely fine strands of sugar are stretched and woven together, leaving a great deal of empty space between them. As a result, cotton candy occupies a large volume while having a relatively small total mass. The two planets orbiting TOI 791 also occupy enormous volumes while containing unusually little matter. But the similarity ends with the comparison in density. They are not made of sugar, they do not have soft surfaces, and they are not porous spheres that could be touched. If a spacecraft could approach a superpuff planet, it would most likely encounter no clear boundary. Far above the deeper interior, the spacecraft might begin passing through extremely sparse particles of gas. As it traveled farther inward, the number of particles would increase, the pressure would rise, and the surrounding environment would gradually become denser. There would be no simple moment resembling a landing on solid ground. The outer layers of a gas planet transition gradually from nearly empty space into a thin atmosphere and then into denser regions below. The boundary measured by a telescope is simply the level at which the atmosphere becomes thick enough to block a significant amount of the star's light. This makes the size of a gas planet different from the size of a rocky planet. Earth has a relatively clear surface where the atmosphere meets oceans and continents. For a world made mostly of gas, the radius is usually defined by a particular pressure level or atmospheric layer rather than by solid ground. If the outer layers of gas are extremely broad and opaque, the planet will block more light during a transit. From Earth, that shadow makes the planet appear very large, but much of its outer volume may contain only extremely thin gas, while the region holding most of its mass lies much deeper inside. We can imagine a quantity of gas held around a relatively small core. Near the core, the gas is compressed more tightly. Farther outward, gravity gradually weakens, pressure decreases, and the gas spreads over a wider region of space. Under the right conditions, these outer layers may expand until the planet becomes nearly the size of Jupiter, even though its total mass is only a few tens of times that of Earth. This is what makes TOI 791b and TOI 791c so difficult to explain. A low-mass planet usually has weaker gravity, so holding onto an enormous atmosphere over long periods is not simple. Radiation from the star can heat the outer gas, causing some particles to move fast enough to gradually escape into space. If the atmosphere continues to lose material, a super-puff planet may shrink over time. Yet these two worlds still appear extremely large. This could mean that they possess unusual internal structures formed under extraordinary conditions or are currently passing through an evolutionary stage that scientists do not yet fully understand. Researchers must also consider the accuracy of every measurement. The masses were inferred from the ways the planets altered one another's transit times. Their radii were estimated from the amount of starlight they blocked. Even a change in the estimated size of the host star, the shapes of the orbits, or the way the data is processed could influence the final results. Even when these uncertainties are taken into account, however, both worlds still belong among the lowest density planets ever found within their size range. More remarkably, they do not exist alone. They orbit the same star. This increases the possibility that the two planets pass through a connected history of formation. They may have formed from the same disk of gas and dust before moving together toward their present orbits. Both may have gathered enormous envelopes of hydrogen and helium while the system was still young. It is also possible that some observational effect is making their radii appear larger than they truly are. But even before exploring those possibilities, the current results are enough to transform the original picture. The two shadows once suggested heavy worlds like Jupiter. Now they appear as enormous spheres of gas, with their mass spread across an almost unimaginable volume. TOI 791b is nearly the size of Jupiter, but weighs less than 10 times as much as Earth. TOI 791c is larger than Jupiter, yet its mass is still equivalent to fewer than 20 Earths. Their gigantic appearance does not come from a gigantic amount of matter. Instead, it may come from the way their outer layers extend far beyond the deeper interior. The farther outward we travel, the thinner the gas may become. Pressure gradually decreases, particles become more widely separated, and the atmosphere slowly blends into the surrounding space. There is no visible line marking where the planet ends and the universe begins. But without a clear surface, where does the size of a gas planet truly end? When we think of a planet, we usually imagine a place with a surface. It might be made of rock, ice, sand, oceans, or broad open plains. no matter how different the environment may be. There is still a relatively clear boundary between the atmosphere above and the solid or liquid material below. But for gaseous planets such as TOI 791b and TOI 791c, that familiar picture no longer applies. These two worlds most likely do not have a clearly defined solid surface where a spacecraft could land. If a probe approached them, it would not see a horizon like the one on Earth, nor would there be a simple moment when landing legs touched the ground and the descent came to an end. The journey downward would begin in a region almost indistinguishable from the surrounding space. There, gas particles would be separated by enormous distances. They would be so sparse that a spacecraft could pass through while feeling almost no resistance. There would be no clear shell surrounding the planet, only an extremely thin region of gas that gradually became denser farther inward. As the spacecraft descended, the number of gas particles within the same amount of space would increase. They would collide more frequently, creating greater pressure. Pressure can be understood simply as the degree to which matter is pushing against a certain area. Air also produces pressure on Earth, but we are so accustomed to it that we barely notice. Inside a gas planet, pressure can rise continuously with depth, eventually reaching levels far beyond anything familiar to us. The temperature could also change. Gas in the outer layers is illuminated by the star, while deeper layers are compressed by the weight of all the material above them. But for the two planets around TOI 791, we still do not know exactly how their temperatures change, how the gas layers move, or what kinds of clouds might exist. These details must remain possibilities awaiting observation, not confirmed images of what the planets are truly like. What is more certain is that density would increase with depth. The outermost region might be extremely thin, but closer to the center, gravity would compress the gas more tightly. Under extreme conditions, the boundary between gas and liquid might no longer be as distinct as it is on Earth. Matter could gradually transition into a denser state without ever crossing a separate solid surface. One possible model suggests that deep inside TOI 791b and TOI 791c, there may be cores rich in rock, ice, or heavier elements. These cores could contain a significant portion of each planet's mass, while broad layers of hydrogen and helium extend far above them. However, we do not yet know the sizes of the cores, their exact compositions, or the nature of the boundaries between them and the surrounding gas. This would make a descent into a gas planet very different from falling toward Earth. On our planet, an object passing through the atmosphere will eventually reach the ground or the ocean. On a superpuff world, a spacecraft might continue sinking through layers of gas that become steadily denser. Resistance would increase, pressure would grow stronger, and the temperature would change, but there would be no impact announcing that a surface had been reached. If the spacecraft were strong enough to continue, the increasingly dense atmosphere might gradually slow it down. Eventually, the pressure could become too great for its structure to withstand. The probe might stop functioning long before it reached the region containing most of the planet's mass. For this reason, the idea of a person standing on TOI 791b or TOI 791c does not fit the structures these worlds may possess. The comparison to cotton candy can also create a misleading image. Cotton candy has a soft surface. It can be held, touched, and pulled apart. These two planets are not porous masses with clearly defined edges. They are more likely made of continuous layers of gas, ranging from extremely sparse on the outside to increasingly dense farther within. Light as cotton candy refers only to the fact that their average mass is extremely low compared with their volume. It does not describe how they would feel to the touch, because there may be nowhere to touch in the ordinary sense. Far enough below the outer atmosphere, the environment could become more violent and extreme than any solid surface. The next difficulty lies in defining the size of a planet with no clear boundary. For Earth, the radius can be measured from the center to the ground or to average sea level. But on a gas planet, The density does not suddenly fall to zero at one specific edge. The atmosphere simply grows thinner and thinner until it blends into space. Astronomers must therefore choose a practical definition. When a planet passes in front of its star, the outer gas layers begin absorbing or scattering some of the starlight. Deeper within the atmosphere, more light is blocked. The observed radius is usually associated with the region where the atmosphere has become thick enough to be nearly opaque to the type of light being measured. This means that the planet's shadow does not necessarily reveal where the dense material begins. It reveals the boundary beyond which starlight can no longer pass through easily. If the atmosphere extends very far outward, the shadow may be much larger than the region containing most of the planet's mass. We can imagine a relatively small core buried deep inside and surrounded by expanded layers of gas. Near the core, the gas is tightly compressed and contains more matter. Farther outward, the density decreases rapidly, but the gas may still block enough light to contribute to the measured size. When the entire outer atmosphere is included in the radius, the planet may appear nearly as large as Jupiter, even though most of its volume contains only extremely thin gas. This may be part of the explanation for the remarkably low densities of the two planets, TOI 791b and TOI 791c do not necessarily have uniform structures from their centers to their outer edges. Their average densities are simply calculated by dividing their total masses by their entire observed volumes. Deep within them, there may be regions that are far denser, while the outer layers extend across an enormous amount of space. A simple image can help explain the difference. Imagine a city where most of the population is concentrated within a small central district, while the administrative boundary extends far outward across almost empty land. If population density is calculated across the entire area, the result will be very low even though the city center remains crowded. Super-puff planets may similarly contain most of their matter deep inside, while their observed radii include extremely sparse gas in the outer regions. But even this image is only an illustration. The true structures of TOI 791b and TOI 791c have never been seen. No spacecraft has passed through their atmospheres. No instrument has directly measured the pressure at different depths. Everything we know comes from the star's light, the gravitational interaction between the planets, and physical models created to explain the data. Those models must answer many questions at once. How large is each planet's core? What percentage of its mass is contained in the atmosphere? Are hydrogen and helium alone enough to produce the observed radius? Are the outer layers gradually escaping into space? How much has each planet contracted since it first formed? For worlds with such low densities, the outer atmosphere may be especially sensitive to temperature and radiation from the star. When gas is heated, its particles move faster and the atmosphere can expand. But if those particles move fast enough, some of the material may also overcome the planet's gravitational pull and escape into space. This creates a delicate balance. The atmosphere must be warm enough to remain inflated, but the planet must also retain it over long periods. Their low masses give them weaker gravity than Jupiter. If the gas escapes too quickly, the planets will gradually shrink. If these two worlds have managed to preserve their extended atmospheres, something in their structures or histories may have slowed the loss of gas. One possibility is that they are still relatively young and have not had enough time to contract completely. Gas planets can be hotter and larger when they first form. As they lose heat over time, they gradually become smaller. If the TOI 791 system is younger than expected, the planet's large sizes may reflect an early stage of their evolution. Another possibility is that their atmospheres contain layers of haze or tiny particles at high altitudes. These particles could block the star's light before it travels into the denser gas below. The planet would then cast a large shadow even though the atmosphere, containing most of its matter, lies much deeper. The observed radius could also be affected by another structure, such as a ring system. But whether the final explanation involves an inflated atmosphere, high-altitude haze, or some feature that has not yet been recognized. The idea of a solid surface still does not accurately describe these two worlds. They may be better understood as regions of matter whose density changes continuously. Outer space gradually becomes atmosphere. The thin atmosphere slowly transitions into denser layers. Those denser layers become increasingly compressed farther below. At the center, there may be a core rich in heavy materials, but even its boundary may not be simple or sharply defined. For observers on Earth, all of this complexity is reduced to a shadow. TESS cannot see the individual atmospheric layers. It records only where the light begins to be blocked. The nearly Jupiter-sized or even larger radii of the two planets may therefore mainly reflect the extent of the gas capable of blocking starlight, rather than the size of any surface hidden below. A world can be enormous without having solid ground. It can possess a gigantic diameter, while most of its outer region contains only thin gas. And during a descent from space into its interior, there may be no moment indicating that someone has truly stepped onto the planet. There would only be an environment that steadily becomes denser, heavier, and more difficult to move through. To preserve atmospheres extending so far into space, these planets may have begun their lives in a place very different from where they are today. To understand how TOI 791b and TOI 791c could have grown so extraordinarily large, we must return to a time before this planetary system even existed. The star at its center was only beginning to form from a cloud of gas and dust collapsing under gravity. Most of the material gathered into the young star, but not all of it fell into the center. Some of the remaining gas and dust continued orbiting around it, gradually spreading into a broad, thin disk. This structure is known as a protoplanetary disk, meaning a region of material surrounding a young star where planets can be born. It consists mainly of hydrogen and helium, the two most abundant elements in the universe. Scattered throughout that enormous amount of gas are tiny grains of dust containing rock, metal, ice, and many other compounds. At first, the dust grains are no larger than particles of smoke or fine sand. They move through the disk, collide with one another, and sometimes stick together. Through countless combinations, the small grains form larger clumps. Those clumps continue gathering material, becoming objects ranging in size from stones to mountains before gradually developing into planetary embryos. This process does not occur evenly throughout the disk. Close to the star, high temperatures prevent many volatile materials from freezing. The solid matter there is made mostly of rock and metal. Farther away, where temperatures are lower, water and other compounds can remain frozen. The additional ice increases the amount of solid material available, allowing planetary cores to grow larger and more quickly. One widely accepted explanation for the formation of giant gas planets is known as the core accretion model. According to this model, a core rich in rock and ice forms first. Once that core reaches a sufficient mass, its gravity begins capturing hydrogen and helium from the surrounding disk. During the early stage, the gaseous envelope grows relatively slowly. The core still accounts for most of the planet's mass, while the surrounding atmosphere is not yet especially thick. But as more gas accumulates, the atmosphere itself adds to the planet's gravitational pull. The collection of material can then accelerate, allowing the planet to draw in large amounts of hydrogen and helium before the disk around the star disappears. It is a race against time. A protoplanetary disk does not last forever. Radiation and winds from the young star gradually drive gas out of the system. Some material falls into the star, while other matter is swept away or gathered into celestial bodies. After several million years, the supply of gas needed to build giant planets may no longer be sufficient. A planet that develops an extensive gaseous envelope, therefore, usually needs three conditions. It must form a core massive enough to hold gas. It must exist in a region where hydrogen and helium are still abundant, and it must grow quickly enough before the protoplanetary disk vanishes. Jupiter may have passed through a similar process. An early core formed within the disk surrounding the young sun and later gathered an enormous amount of gas. The result is the planet we see today, containing more than 300 times Earth's mass and possessing enough gravity to compress its deep atmospheric layers. TOI 791b and TOI 791c do not fit easily into that picture. They are nearly the size of Jupiter or even larger, but contain only a few tens of Earth masses. This suggests that they may have gathered a significant amount of gas compared with their cores, without developing into massive planets like Jupiter. This is where the contradiction begins. If a planet's core is too small, its gravity may not be strong enough to attract and retain an enormous atmosphere. Gas within the disk is constantly moving, is affected by heat, and may easily escape from an object with a weak gravitational pull. A low-mass core would normally retain only a relatively thin gaseous envelope, but if the core were massive enough to collect large amounts of hydrogen and helium, the planet's total mass should also be higher. Once gas begins accumulating rapidly, the process may continue and produce a massive gas giant. TOI 791b and TOI 791c seem to have stopped at an unusual stage. They acquired enough gas to become enormous, but not enough total material to become heavy worlds. One possibility is that the two planets formed farther from the star than their present locations. In the colder regions of the protoplanetary disk, their cores could have grown efficiently because ice and solid material were more abundant. Lower temperatures would also have helped the gas surrounding each core cool and contract, allowing the young planets to continue gathering more from their environment. As gas cools, its particles move more slowly and are more easily held by gravity. An atmosphere that is too hot tends to expand, making it more difficult for the planet to attract additional matter. The distant, colder regions of the disk may therefore have provided more favorable conditions for the planets to build their original atmospheres. But TOI 791b and TOI 791c are no longer located where they may have been born. One hypothesis suggests that after forming farther out, they gradually moved inward. This change in orbit is known as planetary migration. A young planet does not travel through completely empty space. It is surrounded by a disk of gas and dust and continuously exchanges gravitational forces with the material around it. Those interactions can alter its orbit. Over time, the planet may lose some orbital energy and move closer to the star. When several planets migrate through the same disk, they can also influence one another. One world may move inward more quickly, while another travels more slowly. As the distance between them changes, gravity can adjust the motion of both planets and guide them into a linked orbital rhythm. The orbital periods of TOI 791b and TOI 791c are close to a simple ratio. This may be a surviving trace of the time when they migrated together through the gaseous disk. They may have been brought closer to one another before gravity helped maintain a relatively stable relationship between their motions. Moving closer to the star, however, creates another difficulty. As a planet receives more energy, its atmosphere becomes warmer and expands. In the upper layers, some gas particles may move fast enough to overcome the planet's gravity and escape into space. This effect is especially important for low-mass planets because they cannot hold gas as strongly as Jupiter can. If TOI 791b and TOI 791c have remained near their star for a long time, they may have experienced continuous atmospheric loss. Over millions or billions of years, their outer layers should gradually have become thinner, causing their radii to shrink. Yet both planets still appear extremely large today. Perhaps they are losing gas more slowly than expected. The host star may not produce as much damaging radiation as younger, more violently active stars. It is also possible that the planets moved into their present orbits relatively late, after spending the first part of their lives in a colder region. Another possibility is that their gaseous envelopes do not need to contain a very large fraction of their mass in order to create such enormous radii. Hydrogen and helium are very light gases. If they are held under suitable temperatures by relatively weak gravity, the outer layers may spread far beyond the deeper core. During a transit, a telescope measures the region of gas that is thick enough to block starlight. Even a small fraction of the planet's mass contained within an extended atmosphere could therefore greatly increase its observed radius. Most of the matter may be concentrated far below, while the thin outer layers account for most of the planet's volume. Even so, any successful model must explain how such an atmosphere can remain stable. If it is too hot, it will escape quickly. If it is too cold and contracts, the planet will no longer have such a large radius. If the core is too light, gravity will be insufficient. If the core is too massive, the measured total mass will no longer fit. The two planets seem to occupy an extremely narrow balance. They are massive enough to retain material, but not massive enough to resemble Jupiter. They are warm enough for their atmospheres to expand, but perhaps not so hot that the entire outer envelope is stripped away. Their position between these limits is what makes their formation so difficult to reproduce with a simple model. It is also possible that the observed sizes are being influenced by high-altitude haze particles or ring systems surrounding the planets. If these structures block additional light, the true radii of the atmospheres could be smaller than the values inferred from the transits. In that case, the challenge of explaining their formation would become less extreme. But if the two planets truly possess the measured sizes, they are evidence that nature can create worlds very different from those in our solar system. Planet formation depends not only on the initial amount of material, but also on temperature, the timing of gas capture, orbital migration, radiation from the star, and interactions with neighboring planets. TOI 791b and TOI 791c may have begun as small cores in the cold regions of the protoplanetary disk. They gathered hydrogen and helium while gas was still abundant, then migrated inward together. During that journey, they may have retained just enough gas to become enormous worlds without collecting enough additional matter to become massive planets like Jupiter. That is only one possible path. No one can return to observe the TOI 791 system when it was young. The history of its two planets must be reconstructed from the state in which we see them today. Low masses, remarkably large radii, long orbits, and gravitational forces that continue to link their movements. The two worlds remain visible to our telescopes only through their effects, while the process that created them lies deep within the system's past. Each model is an attempt to assemble the surviving clues into a story that remains consistent with the laws of physics. Perhaps the answer lies within an envelope of hydrogen and helium, so extensive that it makes each planet appear far larger than the core hidden beneath it. If TOI 791b and TOI 791c truly are nearly the size of Jupiter, while carrying only a few tens of Earth masses, then the source of their enormous appearance most likely does not lie in a massive core. It may instead come from layers of extremely light gas extending far beyond the denser material deep inside. Hydrogen and helium are the two most abundant elements in the universe. They are also the main components of Jupiter and Saturn. But the way these gases are distributed around a planet depends on many factors: the planet's mass, the temperature of its atmosphere, the age of the system, and the amount of energy it receives from its star. A high-mass planet produces strong gravity, pulling the gas layers closer to the interior and compressing them. This is what happens on Jupiter. Although the planet is made mostly of light elements, it contains so much matter that the gas deep inside is compressed to extremely high densities. The two planets around TOI 791 are different. Their masses are far lower than Jupiter's, so gravity in their outer layers is also weaker. The gas is not pulled downward and compressed to the same degree. Their hydrogen and helium layers may therefore extend much farther outward, creating atmospheres of extraordinary depth. Atmospheric depth does not mean there is a clearly defined upper ceiling. It describes the distance over which the gas density gradually decreases from the deeper interior into space. On a planet with strong gravity, density falls relatively quickly with altitude. But when gravity is weaker, the gas can spread much farther before becoming extremely thin. Temperature also helps determine how far those layers extend. When gas is heated, its particles move faster. They collide more forcefully and tend to occupy a larger volume. The atmosphere therefore expands, much as gas inside a container spreads outward when its temperature rises. On a superpuff planet, relatively weak gravity combined with a warm atmosphere can create enormously extended outer layers. Some of the gas remains bound to the planet, but it is not confined close to the core. It spreads across such a vast region of space that it becomes the main contributor to the radius measured by telescopes. This helps explain how a world only several times more massive than Earth could block an area of starlight nearly as large as Jupiter. The shadow does not come only from the core or the dense gas layers deep below. It also includes the outer atmosphere, where matter is extremely sparse but still thick enough to absorb or scatter the star's light. Some models of superpuff planets suggest that hydrogen and helium may account for more than 20% of the planet's total mass. This would still be less than the mass contained in the core and deeper layers, but because hydrogen and helium are so light, they can occupy a much greater volume. In such a model, the core may be only as wide as a planet far smaller than Jupiter. Around it lies a dense lower atmosphere that gradually transitions into increasingly thin regions farther outward. Most of the observed radius may belong to the atmosphere, while the region containing the greatest amount of matter remains buried near the center. For this reason, the phrase, "an atmosphere larger than the world inside," does not mean that the atmosphere is more massive than everything beneath it. It means that the gas may occupy most of the space covered by the planet. A relatively small core could sit inside a gaseous envelope many times wider than the core itself. From a distance, that difference cannot be seen. TESS records only a single overall silhouette. The telescope cannot distinguish the core from the dense lower atmosphere or the outer layers that nearly blend into space. All of them combine to create one large shadow, making the planet appear to be an enormous world. The two TOI 791 planets belong to a group known as warm gas giants. They receive more energy from their star than Jupiter receives from the Sun, but they do not reach the extreme temperatures of planets known as hot Jupiters. Hot Jupiters are giant gas planets that orbit extremely close to their host stars, sometimes completing an orbit in only a few days. On worlds that are intensely heated, powerful radiation can cause the upper atmosphere to expand dramatically. At the same time, the added energy makes it easier for gas to escape into space. A planet may become highly inflated, but it may also lose material more quickly. TOI 791b and TOI 791c travel along much longer orbits. Their greater distances may protect them from the most extreme heating. Their atmospheres may still be warm enough to expand, while the loss of gas could occur more slowly than it would on planets orbiting very close to their stars. This may be one reason the two worlds have retained such large sizes. They may occupy a relatively unusual temperature range, warm enough for the gas layers to spread far outward, but perhaps not so hot that most of the atmosphere is stripped away over a short period. Even so, equilibrium temperature alone cannot tell the entire story. It is an estimated temperature based on the amount of energy a planet receives from its star and the amount it radiates back into space. It does not reveal the exact temperature at every altitude, nor does it fully describe atmospheric circulation, clouds, or the heat still remaining inside the planet. Young gas planets can retain a great deal of heat from their formation. That heat gradually escapes over millions or billions of years, causing the planet to contract. If TOI 791b and TOI 791c are young, they may not yet have had enough time to cool and shrink to more stable sizes. If the system is old, however, scientists must explain why the two planets have preserved such extensive atmospheres. Some source of energy may be slowing their contraction. It is also possible that current models do not fully describe how heat moves through gas layers of such low density. The composition of the atmospheres is another major question. Hydrogen and helium are the most natural possibilities because they are both light and abundant, but many other molecules may also be present. Water vapor, methane, carbon dioxide, or nitrogen-bearing compounds could leave signatures in the light passing through the outer atmosphere. These molecules would not need to make up most of the atmosphere. Even small amounts could influence how the planet absorbs light, traps heat, or forms clouds. To detect them, astronomers would need to observe the light across many different wavelengths. High-altitude clouds and haze could make measuring atmospheric composition more difficult. Tiny particles suspended in the atmosphere may hide the layers below, like a veil preventing light from traveling deeper. In that case, the observed spectrum could become nearly flat, revealing few clear signatures from individual molecules. But clouds or haze could also help make a planet appear larger. If they exist at very high altitudes and block light efficiently, the radius measured during a transit would extend all the way to the haze layer. The atmosphere below might be slightly smaller than the complete shadow suggests. Another question is whether the outer layers are stable. Hydrogen is the lightest element, so particles at high altitudes may more easily reach speeds high enough to escape the planet. If this process is taking place, the atmosphere could form a stream of material trailing behind the planet along its orbit, although no such structure has yet been confirmed around either of these worlds. The rate of atmospheric loss depends on high-energy radiation from the star, the planet's gravity, and the temperature of its uppermost layers. If only a small fraction of the atmosphere is lost over billions of years, the gaseous envelope may survive for a very long time. But if the rate is higher, the two worlds may be passing through a temporary stage before gradually shrinking. The age of the TOI 791 system is therefore extremely important. Knowing how long the star and its planets have existed would help researchers distinguish between a young state, still inflated after formation, and a structure capable of surviving over much longer timescales. The two planets may also be contracting at different rates. TOI 791c is more massive, so its stronger gravity may allow it to retain gas more effectively. TOI 791b is lighter, yet nearly as large. This could mean that the inner planet's atmosphere makes up a different fraction of its structure, or that the two worlds have not shared exactly the same histories of cooling and atmospheric loss. Although both are described as super-puff planets, they do not necessarily have identical internal structures. One may possess a smaller core and a larger fraction of gas. The other may have a heavier core while still maintaining an extended atmosphere because of its temperature or age. Current measurements provide only the average masses and observed radii. Many different internal structures could still fit between those two values. Scientists must test numerous models, changing the core size, the proportion of hydrogen and helium, the temperature, and the age of each planet to see which arrangements can reproduce what is being observed. If the extended atmosphere hypothesis is correct, TOI 791b and TOI 791c may resemble relatively small cores surrounded by enormous oceans of gas. Most of their volume would lie within extremely thin outer layers, where individual particles are separated by much greater distances than they are deeper inside. Those layers would make the planets appear vast, while also making them fragile. They could expand as they absorb heat, contract as they cool, and slowly leak away into space. The shape of the entire world could change over time, even though the process would unfold far more slowly than a human lifetime. But there is another, stranger possibility. Perhaps those enormous shadows are not produced entirely by the atmospheres. Up to this point, the enormous sizes of TOI 791b and TOI 791c have mainly been explained in one way. The two planets may possess atmospheres of hydrogen and helium, that extend extremely far into space. But the transit method does not actually see the physical boundary of a planet. It measures only the total area blocking the star's light. That limitation opens the door to another possibility. Perhaps part of the shadow does not belong to the atmosphere. When TESS observes a transit, it records how much the star's brightness decreases. From the amount of missing light, astronomers estimate the area of the object passing in front of the star. Then, assuming the object is approximately circular, they can calculate the planet's radius. This method works well when the shadow comes mainly from the planet itself. But if another broad structure surrounding the planet also blocks the light, the inferred radius may be larger than the true size of the world hidden inside. A ring system is one such structure. Within our solar system, Saturn is the most familiar example. Its rings are made of countless fragments of ice, dust, and small pieces of rock moving around the planet. Each individual fragment may be small, but together they form a region extending across hundreds of thousands of kilometers. If Saturn passed in front of the Sun from a suitable viewing angle, the planet itself would not be the only object blocking the light. Its rings would add to the shadow. Depending on their tilt, the total area being obscured could be significantly larger than the circular shape of the planet alone. A ring system surrounding TOI 791b or TOI 791c could produce a similar effect. The planet itself might be smaller than the size estimated from the transit, while the extended rings around it could cause a greater decrease in starlight. From more than 1,000 light-years away, TESS cannot separate the shadow of the planet from the shadow of the rings. Everything blends into the same dimming event. The telescope sees only the star becoming fainter and then gradually returning to normal as the entire structure moves away. The viewing angle would be extremely important. If a ring system were seen almost edge-on, it would appear as only a thin line and would block relatively little light. But if the plane of the rings were tilted more toward Earth, they could appear as a broad region surrounding the planet. Under certain conditions, the complete shadow could resemble a large circular disk. A smaller planet would sit at the center, while the extended ring system would create most of the area blocking the light. If the data were analyzed under the assumption that the entire shadow belonged to a spherical planet, the calculated radius would be larger than the true planetary radius. This would directly affect the estimated density. Density is calculated by dividing mass by volume. The masses of the two planets are estimated from the gravitational influence they exert on each other. But their calculated volumes depend very strongly on their radii. If the radius is overestimated by even a moderate amount, the resulting volume can become much larger. When the same mass is divided by an exaggerated volume, the calculated density becomes lower than the true value. A planet with a less unusual structure could therefore appear to be a superpuff if the shadow of its ring system were included as part of its size. This hypothesis offers a completely different picture. Instead of a small core buried within an atmosphere nearly as wide as Jupiter, there could be a smaller planet surrounded by an enormous ring system. Its gigantic appearance during transit would not fully reflect the internal structure of the planet itself. This does not mean that TOI 791b and TOI 791c definitely possess rings. At present, it is only a possibility that must be tested. Astronomers need to search for subtle features in the light curve that could distinguish a round planet from one surrounded by an extended structure. A nearly spherical planet usually creates a relatively symmetrical transit. The light gradually decreases as the planet moves in, reaches its lowest level, and then rises again in a pattern similar to the beginning. If tilted rings are present, that shape may change. The outer edge of a ring system could begin blocking the star before the planet itself enters. The light would then begin to decrease slightly earlier than expected. As the denser body of the planet moved across the star, the brightness would fall further. Near the end of the event, the rings might continue blocking part of the star even after most of the planet had moved away. These effects could create very small shoulders or changes in slope within the transit curve. If the rings were asymmetrical or tilted at a certain angle, the beginning and end of the transit might not look exactly alike. Recognizing such features, however, would not be easy. The signal from TOI 791 comes from a very distant star. Every small variation can be affected by instrumental noise, Earth's atmosphere during ground-based observations, or natural changes in the star itself. The transits lasting more than 11 hours make the problem even more complicated. To detect a subtle feature near the beginning or end, astronomers need stable observations over a long period. Even one missing section of data could hide the most important detail. The ring hypothesis faces an even greater difficulty. The TOI 791 system contains two planets that both appear to have extremely low densities. If only one planet had an unusually large size, an extensive ring system might offer a relatively natural explanation. But to explain both worlds in the same way, TOI 791b and TOI 791c would each need to possess rings large enough to affect their measured sizes. The rings would also need to be viewed at favorable angles so they could block a significant area. If a ring system were nearly edge-on from Earth, it would not greatly increase the observed radius. For both planets to appear highly inflated, the orientations of both ring systems would also need to be arranged at suitable angles. That is not impossible. Two planets formed within the same disk of material may have related rotational axes and ring planes. If their orbits lie close to the same plane, favorable viewing orientations could occur at the same time. However, rings do not always maintain the same orientation. Gravity from the star, from the neighboring planet, and from any moons could gradually alter the ring plane. Material within the rings could also collide, disperse, or slowly gather into small moons. To preserve an extremely broad ring system over long periods, the structure would have to remain within a sufficiently stable region around the planet. If the particles traveled too far away, the star's gravity could destabilize them. If they were too close, collisions and tidal forces could cause the rings to change more rapidly. Tidal force is the difference in gravitational pull acting on different parts of an object. Close to a planet, this force can prevent material from gathering into a large moon, helping a ring system survive. But the exact structure of rings around exoplanets would still depend on the planet's mass, its distance from the star, and the collision history of the entire system. Another possibility is that the rings, if they exist, are not ancient structures left over from the planet's formation. They may have been created later by a collision between moons or when a smaller celestial body passed too close to the planet and was torn apart by tidal forces. In that case, humanity might be observing the two planets during a special stage in their histories. But explaining why both worlds possessed enormous ring systems at the same time would require a convincing mechanism. The extended atmosphere hypothesis therefore still has several advantages. It is directly connected to the planet's low masses, their temperatures, and their ability to retain hydrogen and helium. But the ring hypothesis reminds us that a shadow does not always provide a perfect representation of the object hidden inside it. Both possibilities might also contribute. A planet could possess an extended atmosphere while also being surrounded by rings. The measured radius would then be the combined result of several different layers of matter, ranging from thin gas to dust and ice orbiting the world. To distinguish between these possibilities, astronomers need more precise transit data. Multiple observations would allow them to combine the light curves, reduce noise, and search for repeating features. If the same unusual signal appeared near the beginning or end of several transits, the likelihood that it represented a real structure would increase. Observations at different wavelengths could also help. An atmosphere usually absorbs light differently depending on wavelength, because each molecule interacts with light in its own way. A ring system made of relatively large opaque particles might block light more evenly. If the planet's measured radius changed noticeably with wavelength, an extended atmosphere would provide a more suitable explanation. If the shadow remained almost the same size, but the light curve displayed the characteristic shape of a non-circular structure, a ring system would become more significant. Whatever the final explanation may be, one fact remains unchanged. Tess has not directly seen either planet. It sees the shadow of everything moving in front of the star. From that shadow, humanity must work backward to identify the object that created it. It may be an enormously inflated sphere of gas. It may be a smaller planet hidden inside a thin but extremely broad ring system. Or the true structure may lie somewhere between those two images, more complex than any single measurement can reveal. From more than 1,000 light-years away, the planet and its rings would blend into the same region of darkness. Every piece of ice, every grain of dust, and every layer of gas would be reduced to a small curve in the data. Yet hidden within that curve, the smallest differences may one day reveal what the two worlds truly look like. Whether their shadows are shaped by atmospheres or rings, both planets are still preserving another secret within the nearly synchronized rhythm of their motion. TOI 791b and TOI 791c do not move independently like two completely separate clocks. They orbit the same star, share the same region of space, and continuously feel each other's gravitational pull. Although they never touch, every orbit of one world leaves a small change in the journey of the other. The inner planet takes about 139 days to complete one orbit. The outer planet needs about 232 days. When astronomers compared these two periods, they noticed that they lie very close to a simple ratio, 5:3. Put more simply, during the time TOI 791c completes nearly 3 orbits around the star, TOI 791b completes nearly 5. After this sequence of motion, the two planets return to relative positions that closely resemble those they occupied before. They do not return to exactly the same locations, but they come close enough for their gravitational interaction to repeat in a recognizable rhythm. A relationship like this is known as a near-orbital resonance. An orbital resonance occurs when the periods of two celestial bodies are close to a ratio made from simple whole numbers, such as 2:1, 3:2, or 5:3. In systems like these, gravity does not act in a completely random way. Its influence can repeat at similar positions after a certain number of orbits. Each time the planets return to a nearly identical arrangement, a small gravitational pull acts in a similar direction. A single interaction may be extremely weak, but when the rhythm repeats over many orbits, the effects can accumulate. One planet may speed up slightly during one part of the cycle and then slow down during another. This is why the transits of the two worlds do not always occur exactly on schedule. TOI 791b may cross in front of the star earlier than predicted when the outer planet pulls it slightly forward. Later, as the positions of both planets change, that gravitational pull may hold it back, causing the next transit to arrive later. TOI 791c experiences a similar influence. Although it is more massive than the inner planet, it is not separate from this gravitational exchange. Each world pulls on the other, and both continually adjust one another's motion during every orbit. We can imagine two people walking along two concentric circular paths. The person on the inner path moves faster and completes more laps. The person on the outer path moves more slowly. After a certain number of laps, both once again approach the same direction relative to the center. At that moment, they do not touch, but if they could pull gently on one another with an invisible thread, the rhythm of both their steps would change slightly. Gravity is that invisible thread. A ratio close to 5:3 does not mean that the two planets are permanently locked into an unchangeable schedule. The word close is important. Their measured orbital periods do not form a perfect 5:3 ratio. They simply lie near that value, close enough for the repeating interactions to become significant. To determine whether the system is truly locked in a stable resonance or merely located near one, astronomers need to observe many more transits. They must follow the timing variations over several years, while also examining the shapes, orientations, and slight deviations of the two orbits. If the system is truly locked in resonance, certain special angles describing the relative positions of the planets would oscillate around a particular value rather than changing freely. At present, however, the available data is not sufficient to reconstruct the complete motion with absolute certainty. Even so, the planet's position near the 5:3 ratio may preserve a trace of the TOI 791 system's past. When the planets first formed, they were not necessarily located in their present orbits. They may have been born farther from the star, within the disk of gas and dust still surrounding the young stellar system. Inside that disk, gas continually influenced the planets. One world could gradually lose orbital energy and move inward. The other could also change position, but not at exactly the same rate. If the distance between them decreased, their mutual gravity could guide the two orbits toward a resonant ratio. Their orbital rhythm could then become a form of balance. Instead of continuing to move toward each other without control, the repeating gravitational interactions could regulate the motion of both planets. One world would pull on the other and then receive a corresponding influence later in the cycle. The system would not become motionless, but it could preserve a relatively stable structure over long periods. This process may explain why TOI 791b and TOI 791c now lie near a 5:3 ratio. They may have migrated through the protoplanetary disk and entered a near-resonant rhythm before the surrounding gas disappeared. Their history, however, may not have followed such a simple path. After the gas disk dispersed, the planets continued to influence one another. Long-term gravitational forces may have shifted the system slightly away from an exact resonance. Tidal effects, the contraction of the planets, or gravitational encounters earlier in the system's history could also have changed their orbital periods. Another possibility is that additional planets once existed or may still exist within the system. They could travel along orbits that do not cross in front of the star from Earth's point of view, leaving no transit signal. Some worlds may also have been thrown out of the system, fallen into the star, or had their orbits altered long before the light we now observe began its journey toward Earth. If other planets once existed, their gravity may have helped arrange TOI 791b and TOI 791c into their present positions. A third world could have caused the two orbits to spread apart, drawn them into resonance, or pushed them away from an exact ratio. For now, this remains only a possibility because there is not enough evidence to confirm another member of the system. These unknowns are what make orbital motion a record of the past. Planets do not preserve memories in the way humans understand them, but their positions, periods, and orbital deviations carry traces of the forces that once acted upon them. By reading those traces, astronomers can attempt to reconstruct the history of the entire system. The near 5:3 rhythm may also help explain why the transit timing variations are large enough to measure. When gravitational interactions repeat in a nearly regular pattern, the small changes do not completely cancel one another. Instead, they accumulate across many orbits, gradually shifting each transit away from a simple schedule. If the two orbital periods had no special relationship, the gravitational pulls might occur in many different arrangements and produce a pattern that was much harder to recognize. But when the ratio lies near a simple fraction, similar configurations return more frequently. This creates a rhythmic signal, like an extremely slow melody, recorded in minutes and days rather than in sound. One beat begins when TOI 791b crosses in front of the star. The planet continues through its second orbit and then its third. Farther away, TOI 791c moves slowly along its longer path. By the time the inner world has completed nearly 5 orbits and the outer world nearly 3, their relationship returns close to its earlier state. The sequence then begins again, but never in exactly the same way. One transit arrives several minutes early, another appears later than expected. Over many years, These differences form a curve that researchers can compare with gravitational models. From that curve, they estimate the masses of the two planets. The orbital rhythm reveals not only how the worlds are moving, but also how strongly they pull on one another. The more massive a planet is, the greater the influence it leaves on its neighbor's schedule. But orbital motion cannot reveal their complete compositions. Gravity tells us how much matter they contain, not whether that matter is made of hydrogen, helium, rock, ice, or other molecules. Two planets could produce the same gravitational pull while possessing very different internal structures. To move beyond that limitation, scientists must return to the light. They must measure not only how much starlight is blocked, but also how the remaining light has been altered by the atmosphere. When a planet passes in front of its star, a small amount of the light can travel through the outer gas layers before continuing toward the telescope. Different molecules tend to absorb different portions of the light. If astronomers can measure those signatures, they may come closer to discovering what the two worlds are truly made of. Their gentle gravitational pulls have allowed us to weigh the two planets. But to learn what they are made of, we must study the light that has passed through their atmospheres. The discovery of TOI 791b and TOI 791c is not the end of the story. Their transits have revealed that the two planets exist, how large they are, how long they take to orbit their star, and how strongly they influence one another through gravity. But those measurements still cannot answer the most important question: what is actually hidden inside those enormous outer layers? To search for an answer, astronomers must continue observing the light of the host star. This time, they are not only measuring how much the brightness decreases, they are also studying how the light changes as it passes through the outer atmosphere of a planet. During a transit, most of the starlight is completely blocked by the body of the planet. However, a very small amount passes through the layers of gas around its edge. Before continuing its journey toward Earth, that light must travel through hydrogen, helium, clouds, haze, and any other molecules present in the atmosphere. Each type of molecule interacts with light in its own way. It absorbs certain wavelengths while allowing others to pass through. A wavelength can be understood simply as a particular portion of light. The visible light, detected by human eyes, occupies only a small region. Beyond it lie infrared light, ultraviolet light, and many other forms of radiation. When light is separated into its individual wavelengths, it forms a spectrum. We can imagine a spectrum as a band of colors extending far beyond those the human eye can see. Within that band, regions absorbed by molecules appear as small signatures. The method of studying light that has passed through a planet's atmosphere is known as transmission spectroscopy. Water vapor can leave one absorption pattern. Methane, a gas made of carbon and hydrogen, creates another. Carbon dioxide also interacts with its own regions of light. Compounds containing carbon, nitrogen, and oxygen may leave additional signatures, allowing astronomers to gradually build a picture of the atmosphere's composition. This does not mean that a single observation will immediately reveal the entire world. The atmospheric signal makes up only a tiny fraction of the star's light. The TOI 791 system is also located more than 1,000 light-years from Earth, making those signatures even fainter. Scientists may need to observe several transits and combine the data to make the signal clearer. The two superpuff planets have one special advantage. If their atmospheres truly extend far into space, the star's light will pass through a larger region of gas. The molecules in those outer layers may still be extremely sparse, but the total distance traveled by the light could be long enough to create a signal that is easier to detect than the atmosphere of a planet whose gas is thin and tightly compressed. The James Webb Space Telescope could be well suited to this work. Webb is especially powerful at observing infrared light, where many atmospheric molecules leave clear signatures. When one of the planets passes in front of the star, the telescope could measure the spectrum before, during, and after the event to identify the portions of light absorbed by the atmosphere. If clear signatures of hydrogen, water vapor, methane, or other molecules are detected, researchers will gain more evidence for testing the extended atmosphere hypothesis. They may be able to estimate the composition, temperature, and relative altitude of the gas layers. Those results could also narrow the range of models describing the size of the core and the amount of gas the planet captured while it was young. But an atmosphere does not always allow its deeper layers to be seen. Clouds or high-altitude haze may block the light before it travels through most of the gas below. The spectrum could then appear faint or nearly featureless, with few clear molecular signatures. A nearly empty result would not necessarily mean that the atmosphere lacks the molecules being searched for. It could mean that a layer of clouds is hiding them. Clouds and haze would themselves provide important information. If they exist at extremely high altitudes, they may contribute to the planet's unusually large measured radius. Tiny particles within the haze could block starlight where the gas is still extremely thin, causing the observed boundary to extend far beyond the denser interior. Observations at several wavelengths could help test this possibility. Small haze particles often affect light differently than transparent gas or larger pieces of matter. If the measured size of the planet changes with wavelength, scientists may find evidence that the atmosphere, clouds, or haze create much of the shadow. On the other hand, if the shadow remains nearly the same size across many wavelengths and shows unusual features near the beginning or end of the transit, the ring system hypothesis may receive greater attention. A broad ring system could block light relatively evenly, while an atmosphere usually produces changes that depend on its chemical composition. More precise data could also be used to search for extremely subtle clues about the shape of the planet. A rapidly rotating world is not perfectly spherical. Its rotation can cause the equatorial region to bulge outward while slightly flattening the poles. This effect is known as rotational flattening or oblateness. If TOI 791b or TOI 791c rotates quickly enough, its slightly flattened shape could influence the light curve during a transit. The signal would be extremely difficult to measure because the planets are so distant and the resulting change would be incredibly small. But if it were detected one day, it could provide clues about the planet's rotation rate and how its mass is distributed internally. The rotation rate would also affect the atmosphere. A rapidly rotating planet may develop wind bands and circulation patterns different from those of a slowly rotating world. Although today's telescopes cannot directly observe the weather on these two planets, knowing their rotation rates would help models describe how heat moves from the day side to the night side. Another question concerns the orientation of the system. Scientists may investigate whether the star's rotational axis is aligned with the orbital plane of the two planets. If the star and the planetary orbits are tilted in different directions, that could preserve evidence of gravitational disturbances in the past. A system that forms calmly within the same disk of gas will generally tend to keep its planetary orbits close to the plane of the star's equator. But the presence of another planet, a close gravitational encounter, or a complicated period of migration could tilt the system. Measuring that orientation would help reconstruct the history through which the two planets have passed. The age of the system must also be determined more precisely. If TOI 791 is still relatively young, the enormous sizes of its two planets may partly come from heat left over from their formation. They may not yet have had enough time to cool and contract. But if the system has existed for billions of years, models will need to explain how such extended atmospheres have survived for so long. The properties of the star may provide clues to its age, its rotation rate, level of magnetic activity, and chemical composition can all be studied. However, determining the age of an individual star is often difficult and may involve a large margin of uncertainty. Several methods usually need to be combined before a reliable estimate can be made. Future telescopes may also search for evidence that the atmospheres are escaping into space. At high altitudes, hydrogen may be heated by radiation from the star and begin moving fast enough to overcome the planet's gravitational pull. If this process is strong enough, the escaping gas could create an extended cloud or a faint tail trailing behind the planet along its orbit. Observations at wavelengths sensitive to hydrogen or helium could help detect this process. If TOI 791b is losing gas more rapidly than TOI 791c, that difference may help explain why the two worlds do not have exactly the same masses, sizes, or internal structures. The rate of atmospheric loss would also reveal how long the superpuff state can survive. The two planets may retain their present forms for billions of years, or they may be passing through a shorter stage of their evolution. If their atmospheres are continuously escaping, these enormous worlds may gradually contract and reveal smaller underlying cores in the distant future. Future transits will also help test the ring hypothesis. A highly precise light curve may show that the shadow is not perfectly circular or reveal small changes before the body of the planet begins crossing the star. If these features repeat across several observations, they could indicate a stable structure surrounding the planet. However, a ring system may also change its orientation over time. If the ring plane gradually tilts under gravitational influences, the depth and shape of the transits may change over many years. Comparing older data with future measurements will show whether the shadow is truly stable. TESS will continue to play an important role in the next stage of research. Although the mission cannot fully analyze the composition of the atmospheres on its own, it can continue recording the times when the two planets cross their star. Every new transit extends the observational record and makes the orbital schedule of the entire system more precise. These additional timing measurements will improve the estimates of the planet's masses. When astronomers know exactly how early or late each planet arrives across many orbits, they can refine their gravitational models and reduce the remaining uncertainty. More precise masses will produce more precise densities, which will help distinguish between different models of the planet's internal structures. If future transits shift in ways that cannot be explained by the two known planets alone, this may suggest the presence of another world. That planet might not pass in front of the star and may therefore never create a visible shadow, but its gravity could still leave a trace in the orbital rhythms of TOI 791b and TOI 791c. Each instrument will contribute a different part of the answer. TESS will continue tracking the timing. Ground-based observatories will measure the light curves and monitor the long transits. The James Webb Space Telescope or other infrared observatories may study the atmospheres. Instruments that measure the motion of the star could search for additional evidence of the planet's masses and any unknown members of the system. No single observation can answer every question, but as the results are placed beside one another, our picture of the two planets will gradually change. From shadows with uncertain structures, they may become worlds whose atmospheric compositions, ages, rates of gas loss, and orbital histories are understood in far greater detail. Future observations may confirm that both worlds possess enormous atmospheres of hydrogen and helium. They may reveal that clouds and haze play a greater role than expected. The ring hypothesis may be strengthened or ruled out. New data may even point toward an explanation that has not yet been considered. This is how an astronomical discovery develops. The first answer often opens the way to many more questions. 2 decreases in starlight were once enough to suggest that planets existed. Years of observations later revealed their unusual periods, sizes, and masses. The next generation of telescopes will attempt to look deeper, moving from their outer silhouettes toward the matter from which they are made. And perhaps, once we learn what these 2 planets truly contain, we will need to change the way we imagine a giant world. For most of human history, the only planets we knew were those within our own solar system. From small rocky worlds like Mercury, to Earth with its oceans and atmosphere, and then to the giant gaseous planets far from the Sun, these worlds form the only planetary pattern we had ever observed. The smaller rocky planets are concentrated in the inner region, where temperatures are higher. Farther out lie Jupiter and Saturn, enormous worlds made mostly of hydrogen and helium. At the outer edge are Uranus and Neptune, smaller than Jupiter, but richer in volatile materials. This arrangement seems so natural that, for a long time, it was easy to imagine that other planetary systems must be organized in much the same way. Jupiter became the familiar model of a giant planet. Its enormous size is accompanied by an equally enormous mass. Powerful gravity holds onto deep, dense layers of gas, while pressures in the interior rise to levels that are difficult to imagine. Looking at Jupiter, it is easy to connect size with mass. The larger a world appears, the more matter it seems it must contain. But the universe is not limited to what exists around the Sunday. Once telescopes began discovering planets around other stars, that familiar picture quickly expanded. Some giant gas planets orbit so close to their stars that an entire year lasts only a few days. Some worlds fall between Earth and Neptune in size, even though our solar system contains no planet exactly like them. Some rocky planets are hot enough for their surfaces to melt, while other worlds travel along distant, frozen orbits. Some small planets may possess atmospheres far thicker than Earth's. Some large worlds have such low masses that their material is spread across an enormous volume. Some systems contain many planets crowded into orbits smaller than Mercury's. Other planets move alone through space, no longer orbiting any star at all. Each new discovery makes the meaning of the word planet broader. TOI 791b and TOI 791c belong to this extraordinary diversity. Their sizes bring Jupiter to mind, but the gravitational interaction between them reveals masses that are far smaller. One world is nearly the size of Jupiter, but weighs less than 10 times as much as Earth. The other is larger than Jupiter, yet still contains less than 20 Earth masses. This contrast does not violate any law of physics. The planets still move under the influence of gravity. Light still crosses space according to familiar rules. Gas still expands when heated, contracts as it loses energy, and may escape from a planet if its particles move fast enough. What is unusual is the way all of these processes come together. Current models can produce gas giants, rocky planets, ice-rich worlds, and many structures that fall between those categories. But to create two planets that are both enormous in size, extremely low in mass, and located beside one another in a system close to a 5:3 orbital ratio, those models must satisfy many conditions at the same time. They must explain how the original cores formed. They must show when the two worlds captured hydrogen and helium, how long that process lasted, and where it occurred within the protoplanetary disk. The models must then describe how the planets migrated to their present orbits, preserved a relatively stable orbital rhythm, and avoided losing most of their atmospheres over time. If the two planets are young, their large sizes may preserve evidence of heat that has not yet escaped. If they are older, their atmospheres must have survived longer than some simple models would predict. If most of the shadow comes from gas, the outer layers must extend across an extraordinary distance. If rings play an important role, both ring systems must have structures and viewing angles suitable for increasing the planet's apparent sizes. No hypothesis should be accepted simply because it sounds appealing. Every possibility must produce signs that observations can test. Atmospheres made of hydrogen and helium would alter starlight in one way. High-altitude haze might make the spectrum appear more muted. A ring system could leave an unusual shape near the beginning and end of a transit. That ability to test each possibility is what keeps the story within the boundaries of science. A mystery cannot simply be described. It must be transformed into specific questions. If the atmospheres are extended, what are they made of? If gas is escaping, how quickly is the material being lost? If the planets possess rings, do their shadows change over time? If the system lies near an orbital resonance, can that rhythm remain stable for millions of years? An unexpected discovery does not weaken science. On the contrary, it places existing models before a new challenge. Those models have successfully explained many worlds, but they must now be tested under conditions that have never been clearly observed before. When a model cannot fully explain the data, it does not mean that everything previously understood was wrong. The model may still work in most cases while missing a small process that had not received enough attention. It is also possible that a factor once considered unimportant, such as high-altitude clouds, the rate of heat loss, or the history of orbital migration, turns out to play a decisive role. TOI 791b and TOI 791c are therefore more than two unusual objects compared to cotton candy. They are tests of how humans understand planetary formation. They force researchers to reconsider the relationships between a planet's core, atmosphere, temperature, mass, and the age of its system. The story began with an incredibly small signal. There were no direct images of the two worlds. No spacecraft had passed through their atmospheres. No samples had been returned to a laboratory. Everything began when the light of a distant star dimmed by a tiny amount. From the depth of that decrease in brightness, astronomers estimated the planet's sizes. From the time between the dimming events, they determined the orbital periods. From the appearance of two separate rhythms, they recognized that the system contained at least two planets. Then the shadows began arriving off schedule. Sometimes they appeared earlier. Sometimes they came later. Those differences revealed that the two planets were pulling on each other through gravity. From the strength of that interaction, their masses gradually emerged. When the masses were placed beside the sizes, the planet's extraordinarily low densities became impossible to ignore. A small dip on a graph led to their radii. Timing measurements gathered over many years led to their masses. And the combination of those two measurements opened a mystery about their internal structures. This is one of the most remarkable features of modern astronomy. Humanity can study a world more than 1,000 light years away without ever seeing it directly. Light and time become tools that help bridge a distance we cannot physically cross. Light reveals how much of the star an object has blocked. Time reveals whether it moves quickly or slowly, and whether it arrives early or late. Gravity connects those changes. Each individual signal is extremely small, but when the pieces are combined correctly, they can reveal an entire planetary system. Every result, however, still carries limitations. The radius depends on the way the atmosphere blocks light. The mass depends on models of the motion of the entire system. Density is an average value and does not fully describe how matter is distributed from the core to the outer atmosphere. The numbers are therefore not the final image of the planets. They are doorways leading toward deeper questions. Perhaps these two worlds contain small cores wrapped in enormous layers of hydrogen and helium. The outer gas may account for very little of the total mass while occupying most of the measured radius. Haze, clouds, or rings may also be making the shadows appear wider than the planets themselves. Future observations will gradually narrow these possibilities. Some hypotheses may be ruled out. Others will become more convincing. And a structure that no one has yet considered may emerge from the data. Whatever the final answer may be, the two planets have shown that nature does not need to follow a single design. Using the same basic materials, hydrogen, helium, rock, and ice, the universe can create countless kinds of worlds simply by changing their proportions, temperatures, timing, and locations. A core that forms early may gather a large amount of gas. A core that forms later may retain only a thin envelope. A planet close to its star may lose its atmosphere. A more distant planet may preserve colder layers of gas. Interactions with neighboring worlds may alter an orbit, drive a planet inward, or hold two planets within a shared rhythm lasting for immense periods of time. A single small change in the early history of a system can produce a completely different outcome billions of years later. Two systems that begin within similar clouds of gas may not create similar planets. A collision, a period of orbital migration, or the exact moment when the surrounding gas disk disappears may determine everything that follows. Our solar system is therefore no longer a required blueprint for every other system. It is one example among countless possibilities. Earth, Jupiter, and the other familiar planets helped humanity ask its first questions. But the worlds around distant stars are expanding the range of possible answers. TOI 791b and TOI 791c do not make Jupiter any less extraordinary. They simply show that a planet with a Jupiter-like size does not necessarily have the same structure or mass. Similar shadows can conceal completely different worlds. In one system, the shadow may belong to a massive planet whose gas is deeply compressed. In another, it may come from an extended atmosphere surrounding a lightweight core. Somewhere else, rings, clouds, or structures not yet understood may alter the boundaries seen by a telescope. This diversity makes planetary classification both useful and permanently incomplete. Names such as rocky planet, gas giant, and superpuff help us organize what we know. But nature does not always create clear boundaries between categories. Many worlds exist within the transitions, carrying the characteristics of several types at once. Perhaps one day, when the atmospheres of these two planets have been studied in greater detail, the name superpuff will still be appropriate. Or perhaps it will prove to describe only their appearance rather than their true structures. Science is always prepared to change its language when new data reveals a more accurate picture. For now, the two planets continue moving around their host star. TOI 791b completes its orbit more quickly. TOI 791c travels slowly along the outer path. After nearly 5 orbits of the inner world and 3 of the outer world, they return to an arrangement resembling the one they occupied before. Each time this happens, gravity gently alters both orbits again. One planet arrives slightly early, the other slows down. Those tiny changes continue to be written into the light leaving the system. The two worlds do not know that their shadows have reached Earth. They do not know that humans have named them, measured their orbital periods, or attempted to calculate their masses. For them, there was no moment of discovery. There is only the continuous motion around a star. New light continues to leave TOI 791 every second. Some of it travels directly into space. Some of it is occasionally blocked by the planets. Those signals begin journeys lasting more than 1,000 years before they can reach the telescopes of a generation living far in the future. By then, the planetary system may have changed slightly. The gas layers may have continued to contract or escape. The orbits may have shifted very slowly, but within every ray of light, there will still be a trace of the state the system carried at the moment that light departed. And there, the two enormous worlds will continue drifting in silence, lighter than anything their vast sizes once seemed to suggest.